Hello and welcome. This is the first part of a two-part lecture on structures and pointers. Here is a quick recap of some of the relevant topics we have already studied. We have studied about structures as collections of variables, arrays and other structures. We have seen how to statically declare variables or arrays of structure types. We have also seen how to access members of structures. In earlier lectures on pointers, we had also studied about the organization of main memory, particularly about locations in memory and their addresses, and in our lectures on pointers we had studied about pointers to variables as well as arrays of basic data types like integer, float, character and the like. In this lecture we are going to study about pointers to variables of structure types, and we are also going to see how to access members of structures through pointers. So let us quickly recall the organization of memory and addresses of memory locations. So main memory can be thought of as a sequence of physical storage locations as is depicted here. Each of these locations stores 1 byte or 8 bits as is shown here. Each horizontal rectangle can be thought of as one location of memory storing 8 bits, and these 8 bits will also be called the content or value of that location. Each physical memory location is also identified by a unique address which can be thought of as the sequence, as the index of that memory location in the sequence of memory locations. So for example, this particular location has an address 409 in hexadecimal, and the content of that memory location is all zeros. If you also recall from our earlier lectures, we had said that when a program executes, or in other words when a process runs, the operating system allocates a part of main memory for use by the process. So if this is the main memory, the operating system might have allocated this part of it for use by the process. Now this memory in turn is divided into 3 segments: the code segment which stores the executable instructions in the program, the data segment for dynamically allocated data, and the stack segment which basically stores the call stack which has the activation records of all functions that are called in the program, and each activation record, if you recall, has memory allocated for all local variables of the corresponding function. So let us quickly see how structures are going to be laid out in main memory. So here is a simple program. This is the main function within which I have declared a structured data type, my struct type. This has 3 members. Member z is of type character, members x and y are of type int, and then I have a variable p1 of structure type my struct type, and I also have a variable a of type int. Now we know that every integer variable needs 4 bytes of storage, so I can visualize the main memory, and the main memory here is divided into 3 segments: the code segment, data segment and stack segment. A being a local variable of the function main, memory for A will be allocated in the activation record for main when main is called by the operating system, and this activation record will reside in the call stack in the stack segment. So therefore memory for A is really allocated in the stack segment, and since we need 4 bytes and since each location of main memory stores just only 1 byte, we have 4 consecutive locations here allocated for the integer variable A. Now how much storage do we need for the variable P1? Well, if you look at the definition of my struct type, you will see that I need 1 byte for the member Z and I need 4 bytes each for the members x and y. Therefore I need a total of 9 bytes of storage. Once again, this being a local variable of main, storage for this will be allocated in the activation record for main, which will be stored in the call stack which resides in the stack segment. So in the stack segment I will have storage for P1, and in that storage I will have a byte reserved for P1.z and 4 bytes each reserved for P1.x and P1.y. Note that I am saying that this is the amount of memory allocated for P1, whereas P1.z required 1 byte here, P1.x and P1.y required 4 bytes at each of these places. So there is still some gap here. So if you are wondering what is that gap or padding, let us just wait for a few slides. But for the time being, let us note that since P1 and A are both local variables of main, therefore memory for both P1 and A have been allocated in the activation record of main in the call stack which resides in the stack segment. Now in order to understand a little bit more about this gap or padding here, we must first ask what can we safely assume about the memory layout of structures when I have variables of structure types in my program. So, here is my structure type, my struct type, and here is the variable, and here is the memory layout that we have already seen. What can we safely assume about this memory layout when programming in C++? Well, we must not make any assumptions about the relative layout of different members within the memory allocated for a structure. So, while it may be reasonable to assume that the memory for P1.z will be allocated immediately before the memory for P1.x and then the memory for P1.y, because they appeared in that order in the definition of my struct type. However, it is not safe to assume this in general when you are programming in C++. So, we will make no assumptions that P1.z appears before P1.x and that appears before P1.y. We will make no such assumptions about the layout of the structure in main memory. We are also not going to make any assumptions about whether there are paddings or gaps or unused memory locations after the locations allocated for different members of a structure. For example, we will not assume that there is no gap or unused memory location between the location allocated for P1.z and the first location allocated for P1.x. Similarly, we will not assume that there is no gap or padding or unused memory location between the last location allocated for P1.x and the first location allocated for P1.y. For example, this should also be a perfectly alright memory layout for my struct type as far as our program is concerned. So, we must not make any assumptions about the absence or presence of gaps or paddings between the memory locations allocated for different members of a structure. However, we can assume that the memory locations allocated for a particular member like P1.x are all going to be contiguous, they are going to have consecutive addresses. So, for example, we can assume that P1.x will be stored in 4 contiguous locations and similarly P1.y will be stored in 4 contiguous locations. We cannot assume and we should not assume that there will be no gaps or paddings between P1.x and P1.y, and similarly we must not assume that P1.x will be stored earlier in the address space than P1.y. Well, now that we know how structures are laid out in memory and what we can and cannot assume about them, let us try to see how we are going to find out addresses of structures in memory and how we are going to use these addresses to access these structures in memory. Now, if you recall, we had the ampersand and star operators which we had used with variables of basic data types. For example, here is a little program fragment and here int star basically refers to a pointer data type, specifically pointer to an integer data type, and in this assignment statement ampersand a is asking the computer to take the address of the starting location of variable a which is of type int. Since variable a is of type int, we need 4 locations for storing the value of a. So, ampersand a will give us the address of the starting location of variable a and that will be assigned to pointer a. And similarly, when we say star pointer a, we are telling the computer to look at the contents of the memory locations whose starting address is given by pointer a, and we should look at these contents as an integer because pointer a is a pointer to an integer. Pointer a has been declared to be of the type pointer to integer. So, when I say star pointer a, I am saying the contents as integer of the memory locations whose starting address is given by pointer a, and those contents of those memory locations should be updated to the value 10. Now, it turns out in C++ we can use the ampersand and star operators in exactly the same way with variables of structure types. So, here is a little C++ program fragment which uses the ampersand and star operator with structure types. So, here is our mystruct type that we have seen earlier. P1 is a variable of structure type mystruct type. Pointer P1 is a variable which is of type pointer to mystruct type. So, just like int star says it is a pointer to an integer, so mystruct type star says that it is a pointer to mystruct type. Mystruct type is a structure type and mystruct type star is a pointer to that structure type. Similarly, when we say ampersand P1, we are saying take the address of the starting location of variable P1, which in this case happens to be of type mystruct type. And similarly, when we say star pointer P1, we are asking the computer to update through this assignment statement the contents of the memory locations whose starting address is given by pointer P1, and these contents should be thought of as having the value of a variable of type mystruct type. Because pointer P1 is declared to be of type pointer to mystruct type, therefore star pointer P1 should be treated like an object of type mystruct type, and we should treat the contents of the memory locations whose starting address is given by pointer P1 as being the value of an object of type mystruct type. So in this case, that object of type mystruct type is being initialized to C23. We have already seen initialization of structures earlier. It means the member Z of the object star pointer P1 will be initialized to the character C, and X and Y, the members X and Y of the object star pointer P1 will be initialized to 2 and 3 respectively. Now that we have seen how to find out addresses of structures and how to dereference those addresses, we want to ask, can we access the member of a structure like P1.x through a pointer to that structure like pointer P1? Well, the answer to this is yes, and by the obvious way, since star pointer P1 was allowing us to access the contents of the memory locations whose starting address was given by P1, and these contents were being accessed as an object of type mystruct type. So I could simply say star pointer P1.x, and I will be accessing the member X of the object star pointer P1. So I could have this assignment statement in which I am accessing the member X of the object star pointer P1 and updating it to 1 plus the value of member Y of the object star pointer P1. Now in C++, the way to read this is that star pointer P1 is an object of type mystruct type. So star pointer P1.x is the member X of that object. And C++ actually provides a separate operator for situations like this. For example, instead of saying star pointer P1.x, I could say pointer P1 arrow x, and instead of saying star pointer P1.y, I could say pointer P1 arrow y. So in general, a pointer variable arrow member name is the same as star pointer variable. Basically dereference the pointer variable and find out the entire structure that the pointer variable is pointing to, and then access member name of that structure. So here is our original program in which I had initialized star pointer P1 to C23 and then added 1 to star pointer P1.y and used it to update star pointer P1.x. Here is a completely equivalent program where I have initialized the members Z, X and Y of P1 by using the arrow operator. So pointer P1 is assigned the address of P1, and then I can use the arrow operator in this manner. Pointer P1 arrow Z is assigned C, pointer P1 arrow X is assigned 2, pointer P1 arrow Y is assigned 3. This will basically initialize P1 to the values C for Z, 2 for X and 3 for Y, and then instead of using this star pointer P1.x and star pointer P1.y, I could rewrite this assignment statement using the arrow operators like this. So these are two completely functionally equivalent program fragments. So in summary, in this lecture, we studied about pointers to variables of structured data types. We saw the use of the ampersand and star operators with structures, and we also saw the use of the arrow operator to access members of structures through pointers. Thank you.